support. I have 3 grants running. It's usually $16 to $18 an hour, and for the NSF one, it supports food as well and housing. Jeez. So it's a very strong support. And the projects, let me show you really quick. And I'm considering mentor a master students here as well. If one of you are interested, I'm gonna request it from the, let me see. Do I still have it? Give me a second, real quick. Sorry. All right, so I gave a talk during the conference, during the break, and there are so many things going on, but definitely there's no time to go through that. I have like 4 to 5 lab space, which is way bigger than whoever over here in the department. And students are spoiled. They have dedicated space, interdisciplinary, electronics, optics, even biology. So we are doing a lot of research on all different kinds of things, but one of them is detecting bacteria from environmental water samples. We sample water and detect it. So we design the instruments by ourselves. It's optical with a thermocycler to amplify the DNA in it. So students learn how to do the PID controller, the microcontroller stuff, programming, interface, C++, SDL in a Raspberry Pi touchpad, so they can control all the thermal cycle loops. That's one of the projects getting supported. And so this is a machine we designed. We are trying to sell it in the future, but it's being supported by NSF and EP as well. So you can see this is a GUI, a GUI designed by a former student. So it's a C++ based in Raspberry Pi. They are able to move the protocols in here and drag and drop in here. It's very similar to whatever the GUI you design for motor vehicles. It's like a little touchpad, right? So it's very similar kind of project. If you learn how to do this, you should be able to know how to design a little interface for that touchpad in the car as well. It could be a very good experience to have. And so these are, this is the temperature sensor network. You know, if you use the ESP32, you can do a lot of fancy stuff, including Wi-Fi. So we are able to implement Wi-Fi to all these temperature sensors. And I'm going to put this in the embedded class, a similar class here in Florence College, which is ESP32 programming with a Wi-Fi capability, and eventually students will design a Android app which is able to change the Wi-Fi password and monitor the temperature sensor as well. But this is a product we sold to the Puxa Springs, Puxa Springs hot tubs. There are 24 hot tubs. They want to wirelessly monitor the temperature instead of manually changing the temperature by their staff members. So we already delivered to the company with the Android app. It's being put on the Samsung touchpad and directly delivered as well. So they are able to monitor temperature, looking at the little windows with 24 hot tubs, and change the Wi-Fi, which is seems to be pretty simple, but actually it took us probably 50% of the time for the research and for the R&D. So, for example, the Wi-Fi changes on the property because they want to change it over time. So how to change it through the terminal monitor, right? So that's could be challenging. There's no way to do it with PIC. It takes like 2 years. But with the ESP32, we are able to make it fancier through that Android app. This is a horse project. We are trying to detect a horse lamines with a sensor, but this won't be a project in the summer next year because it's not funded. It was not funded. We applied it, but eventually got rejected. This is a high voltage generator with a add mega microcontroller with it, and transformers, and eventually amplify the signal with the voltage multipliers, eventually getting plus minus 3,000 volts. It's going to be used as a air cleaner for motor vehicles, and the company GPS is trying to buy this product from us, and will be sold to Toyota and Tesla in the future, hopefully. That will be rich. I will just retire after that. So this is patented, and it's just one of the projects. Another one is a feature project, like I told you guys, is keeping me up daily. It's a super unique, only one in this country, which is integrated circuit design, and with the industry standard tools called Cadence, Virtuoso, plus Innovus. So if you go to Apple, Samsung, you need to know Innovus. or NVIDIA. If you want to just get a $90,000 job, you don't have to know Cadence. If you want to get like 150 as a start salary with NVIDIA, you have to know how to work with integrated circuits in Innovus. And Fuller's College is the only institution in this state in Colorado has Innovus and Genus installed in the server. So students will be able to connect to the server and do integrated circuit design. So I'll show you a picture. That's why, here is a wire bonder. That's the chip, right? If you etch off the epoxy of the PIC chip on the board, you'll see a little silicon die like this. It's 1.5 by 1.5 millimeters, super tiny silicon, and can integrate like billions of transistors in the same area. That's why your PIC chip can do so many different things. And so what we do here is, so this is just one of the microelectronic class in the Sir Hunter level class in junior year. So we design the op-amp and we send it to Moses, get a chip and place it in the package, and then we do the wire bonding. I purchased the wire bonder, $25,000, and we were able to do all the connections. So all the little tiny holes over here is about 75 micrometer, and under the microscope, you are able to do all the connections to the pads, right? And the pads are connected to the pins, and you insert the pins to the breadboard so you can receive signal and inject signal to the chip. So this is the chip, this is the die. See how tiny it is? This is like the micro chip on the board, on the PCB board, and that's the die. You probably have never seen the die in the past, right? This is the silicon die directly from sand. They convert it to silicon wafers and eventually get a chip out of it. It has like billions of transistors in it. Okay, so that's why I'm super excited, because we are the only institution right now doing this for undergraduates. There are 4 in the country are doing that. We are one of them. And the reason making this super excited, I'll let you know, because next year, even though this is not directly funded by the NSF grants, but if you want to do that with me, okay, but you have to do well in this class first, so I know you can do things. And then I'll fund you for the whole summer to work on this integrated circuit design, okay? So what is that? It's so this guy invented the 6502 microcontroller, which is a little bit older than PIC, and he converted everything into IPGA-based chip by converting all the manual layout, which he did in 1980s. He manually laid out and drew all these transistors by hand on a big poster paper like that. So the chip takes that much area, and I don't know how they did it, but eventually printed onto the chip. So they didn't have all these industry level EDAs to convert everything to Verilog by the time. But now they hired another guy, a digital engineer, convert everything to a Verilog and eventually implement it to IPGA. However, they have to purchase IPGAs from Intel and then resell it. It costs more money. So the goal is to convert everything into a dedicated ASIC. So you design it by yourself and then fabricate it through TSMC, okay? And Mills, based in Denver, is the only company in the country doing this kind of business in the affordable level. So we are working with Mills to get this done. So this is our chip. It's a 6502 chip. It's already 90% there. I got one student hired, undergraduates like you guys, but senior level. He is doing this as a senior seminar project. You see, what are these? What are these? If you zoom in, you couldn't even see, right? These are transistors. So that's memory cells and 2 RAMs being compiled by the memory compiler from a dedicated machine that is probably, I don't know whoever still has it, but I just purchased it, which is able to compile the memories under the TSMC 180 nanometer technology. And so the memory is taking a lot of space. And these are the core CPUs and all these digital circuits in there. And these are the pads, okay, the pads. So that's the whole silicon die, like the one you saw in the previous slide. So eventually we'll receive this from TSMC and bond it to the chip. So the idea is students will learn how to design chips like this from scratch, from nothing, like Verilog, all right? And get the chip done. You know what is this? Like I reminded you about it. So this guy implemented this design in Apple II computer in 1980s or 1990s. Apple II computer, it's a commercial product, okay? Which means this is a microcontroller. So I'm going to teach my microcontroller class in the future using our chips instead of buying all these pigs. So that's the most exciting thing can happen in this field, in undergraduate education for microelectronics. Super unique, only one existing. This is a Department of Transportation project. I have money to support as well if you are more interested in this one. So we are building a boat and eventually convert it to underwater vehicle to monitor the riverbed. Sometimes they're getting erosion and scour under the bridge piers, and so we want to design. I have money, so if you want to do this instead, I will be able to pay you to, full time, depending on your interest. But this is the most exciting part, and I want to get capable students. Oh, but you have to take VLSI first. Have you taken VLSI in the past?
VLSI is only offered next semester.
After next semester,
A good amount of us are planning on taking it.
Okay. But I'm willing to train you on it. I mean, that could be challenging. Probably do this instead. I mean, it's difficult to understand the details if you don't know VLSI. But possibly in the future, after you finish VLSI, reach out to me. I think I can remember the good ones over here. And so I'm going to give you the bonus points for the quizzes on Fridays. They are not be counted as your towards your grade. Just keep that in mind, okay? I just want to improve the attendance, since if you don't come to the class, you won't learn things and you feel bad about the class. Eventually, we're just failing each other. So very short, like 5 minutes quizzes, not quizzes, 5 minutes in class exercise. So you don't have to take it in the testing center. It's because it's not a quizzes. It's not counted towards your grade, okay? Bonus points. You do it, helps you prepare your final exam, because these problems will be very similar to the problem in the final exam. That's the goal, okay? That's the incentive to keep you here in the class. Any question on anything before we move forward?
Did you find an I2C protocol for those OLED displays?
Oh, it's a SPI. It's not I2C. It's a SPI. I plan on doing that for you guys as well if I got time, because we only have how many labs? Let me see. 8 and 9, right? So look at the schedule. Just remind you guys one more time. All right. So tomorrow, keep in mind, tomorrow, even though you can demo your Lab7, but it's not required. So Lab7 is due next Wednesday, right? Next Wednesday. But if you are ready to demo Lab7, feel free to do so on Thursday tomorrow. It's called Lab8 for this class, but it's not Lab8 on Dr. Carlson's website. Does that make sense? It's the 8th lab of my class. What do you do tomorrow? Follow the PCB project for your board. Go through this. I will be there for the first section, so you'll get helped. And for the following sections, all the TAs, I know they already took the PCB class in the past. So they should be able to help you guys as well, but I will try to do my best to be there for the following sections as well. Make sense? So that's the hardware person on the team. What about the software person on the team, which you can do? Working on the software flowchart for your design, okay? Proposal as well. And also, if you are done with the software, you can test it on your dev board. So the board you have. Okay? You can have 2 boards, remote controlling one to each other, to the other one, whatever kind of project you wanna work on. Make sense? One software person, one hardware person work together, get a project done tomorrow, or planned tomorrow. And Friday will be ADCs, okay, analog digital converters. We'll prepare you guys for the microphone project in the following week. So Lab 11.9. So Lab 9 will teach you how to use the SD card. So I think after the SD card thing, you guys should be ready to play with whatever available on the board. You can add SD card features to your design, to your project. You can add microphone features to it. So we don't have to do Lab 10 and 11. I think they used to have 10, 11, and a soldering project as well. I don't think that's very helpful, because we are doing our project with soldering on the board at the same time. So we don't have to do that one. Any questions on the plan for tomorrow? No? You're good on that? Okay. So you are supposed to demonstrate your Lab7 win here, right? Next Thursday. Make sense? So Lab 8 is already posted. My step-by-step instructions are already posted. Lab 9 is halfway done. Then I will, finish all the labs I have to do. Okay, and eventually, the following ones will be the SPI, I2C protocols, and sensors, actuators, and whatever the keyboards on Dr. Carlson's website. I'll add some other things that I think are important, like you guys should know. And then we are pretty much done for the semester. Okay, I enjoyed it, but a lot of you didn't. I'm sorry for that if you didn't enjoy this class, but let me know if you have any comments, inputs, feedback. Feel free to just let me know. I will try to improve and fix it. We'll still have like 5 to 6 weeks to go. Okay, I'll do my best. Anything else before I move forward? All right. Here. Lab 7's template. Some of you already finished it. I'm sorry, it's probably wasting your time, but I don't think so, because there's one thing I want to talk about, discuss with you guys. Okay. So, what should we do first? Let's do let's think about the big picture first. So Lab 7, there's no significant difference between Lab 6 and Lab 7. Have you read about the details, the tasks about Lab 7 yet? What's the difference? Could you tell me? Anything different?
You're gonna use a ISR to control the transmitting.
Yes. Okay, that's one of the differences.
One other difference I noticed was you have X and capital X perform like show what's in the transmit and receive buffer.
To toggle the flag, right?
Yeah.
Yeah. Okay. So the transmission, the way to transmit data is a little bit different. So in the previous labs, including the in lab and Lab 6, they use a function, dedicated function called transmission whatever. So that function is being called inside a loop. So it's being called every time when you increment the index, right? So all the single byte characters are being sent one by one. But Lab 7 requires you to use a state machine. So let's look at the template over here, this big picture of the code. So how many ISRs do you have? Let me bring everyone to the same page first. I know the gold standard of teaching well is to repeat as many times as you as you want. Okay. All right. Sorry, I have to repeat this really quick. All right. So what's really happening here? Start from here. If you want to do well in this class, you have to really feel what's really happening inside the chip. Make the physical connection between your brain to the computer, right? Whenever it clocks, you shakes and clocks, so you feel what's really happening, right? So.
It's 2 mega you have in the C.
All right.
Awesome.
That's kind of feeling you should own. So you own this example, you own the code. What's really happening here? I want to show you the code instead, actually. Let me do this first. So the message, the M part of it, it's not a secret, so I don't mind to show you. I even find out if I showed all the entire code, the solution to you guys, you still have problems. So why do I have to make a template? You have problem with MCCs, you have problem with the board, you have problem with LEDs. Okay. I'm improving, right? So you can tell at the very beginning, I just give you a picture. So at the very beginning, I give you nothing. I let you program from scratch. Then I give you a picture, right? Then I give you a PDF. See, the Lab 7 has a PDF, right? Next time will be the whole solution. And I'll still have 10 students visiting during office hours. Oh, it's not working, MCC or something else. Okay. All right, so let's see if you can feel the code. You can own the code yourself. What's happening? So first step, M, right? You have to do M first. To do what? To type the message as the beginning part of it. What's happening here? Are you familiar with this piece of code?
Yeah.
Yeah, you should be, okay? So keep that in mind. The bonus points could be all these critical snippet of code in the future that I will let you fill in, right? Because they are super important. And if I see like most of you guys can successfully fill in all the missing parts in the code snippets in the future, I'm gonna put on the final exam. Hasn't been determined yet, okay? If you can do it, I'll put on the final exam. I'll repeat it multiple times until you can do it.
Because you started too.
Okay, so what's happening? So when you type hello, right? Type hello. You type H. You type H, you see an H in the monitor, right? What's happening? It's printing. Who is printing? Pick is printing, right? So can you feel it right now? Slow it down, right? Slow motion. What's happening? You type. What's happening? Electricity goes to the pig, right? So pig receive it, turn it back. So you'll see H in the monitor. Make sense? That's what happens. If you don't print it, what's happening? If you don't type, what's happening?
You aren't seeing anything.
You won't see anything. What's happening there in the chip?
Still recording it?
Yeah.
What?
Like it's collecting a character still? If we start one?
No, it's waiting at where?
Till you
Command
return.
equals you start one to.
Yeah.
Waiting here.
Till you return.
Why?
If you start reading commands or something.
Yeah, the reading function is really interesting. The reading function, if nothing is received, it's waiting there until it receives something and then read. I talked about this for once, I think in one of the lectures when we introduced this first time.
Yeah.
So it's waiting here. It's waiting here. Is that interesting?
Yeah.
Okay, it's waiting there. So you type, something transmit. If you don't type, it's waiting there. Waiting where? Waiting here. Okay? So if you type again, what's gonna happen? If you type again, it's gonna check this first.
Yep.
Because this guy received something and put it here and then check. So for example, it's not a null yet. Okay, something else. It checks, it passes the check, and do this as well. It's a very simple check as well.
Yeah.
And then go through the materials, the lines in the while loop. So you type, come back. You type, come back. Make sense?
Yeah.
Okay. Otherwise, it's waiting until when? You type what?
Enter.
Enter.
Yep.
Carriage. Then what?
Breaks the one.
It doesn't pass this check.
Breaks
Skip.
the loop, yeah.
Okay? We'll get out from this while loop. Then do what?
Then you pad it with the transfer.
Yeah, the data is done. The string is done. Just add a null, package it, done.
Done.
Make sense? Okay?
Good package right now.
That's the whole process. So where's the string? It's stored in this array.
Yep.
Okay? Then what's next? What's next? So when you are typing, you got for Lab07, you have two ISRs. You have two ISRs. So what are ISRs? Interrupt service routine. If you set a timer, no matter what, they are going to interrupt. No matter what you are doing, even when you are typing, you just didn't feel it. You didn't realize it. It's just like when you're typing, it's running all the while loop over there. However, because you set up an interrupt routine, it's going to interrupt and then come back later because all these materials on the top will be stored in the stack, right? So that's after it comes back, you will take out from the stack and rerun them. But you are not losing anything, okay? But eventually, it will come back. But however, it's going to interrupt, do the ISR, and come back. So you have two ISRs in Lab7. See? What's the first ISR?
Timer one ISR.
My ISR. So my ISR is the timer 1 ISR. Okay? So how do you do a timer 1 ISR though? Set up a timer 1. A certain period, a certain amount of time. It's going to interrupt no matter what. Whenever the flag got turned on, it interrupts. All right? So how to control it when you're typing? I'm not ready yet, just type the H in hello, right? H, interrupts.
You have to have a flag.
You have to have a flag.
Yeah.
Okay? So what controls the flag? Whatever you want to do, doesn't matter. Do you want to keep the flag in M case? You can't, right?
No.
Why
Let's
not?
speak global so that timer 1 ISR can see it too.
But I mean, if you keep it M, you could also
Then you
keep it
can't
global,
interrupt it when
right?
You're trying to type though.
So whenever you finish, right? So when you press enter, oh, okay. So these are not provided in template. That's all right. I don't care. So after finishes this and get out from the while loop and comes here, can you set a flag over here? I think you can. Just try it if you're interested doing that. But I mean, you want to have a better way to control it. So after M, you press enter. You want to wait a little bit because you need a coffee, for example, right? So you want to come back and press S later. You don't want to send it right after you finish the string. Okay, you want to take a coffee break. So then you come back. You think you are ready emotionally. Since you don't want to fail yourself, you don't want to see like something is failing, right? So you're anxious. And then you press Shift S, the flag is on. When the flag is on, interrupt will be valid because you are always checking the flag. You are checking the flag where?
Right there.
Here. Okay? First solution provided for you guys. If the flag is true, okay? So where do you put the flag?
In S.
Yeah, see, there's a little S. Where's S? Here, right? You press S, it does nothing but turn on the flag.
Yeah.
Okay. So, oh, one more question. So if the flag is not true, is it still interrupting?
Yeah.
Yeah. But it's staying at the idle state. It's not doing anything. It's not even entering this if statement because you are transition the states within that if statement. So if it's not getting to the if statement, the state is not changing, it's not updating the state. Every time it interrupts, it's getting to the idle state, but skipping all these cases and break. Doesn't do anything, okay? Make sense for the M? All right, so the UART 2 interrupt. What is this doing here? What is this UART 2 doing here? I mean, if you are still working on Lab 6 for some reason, I think this is the same code that you can use for Lab 6 provided. Okay, so this is how you read from the UART. Why we are not using UART read because it's gonna hold it there like what we talk about. It's gonna hold there. Okay, but if you directly just read it from the register, it will clear the flag and work nicely. So provide it and you don't have to do anything here, just directly use it. So now let's come back to this ISR. Okay. So what is this ISR doing? What is this exactly doing? Transmission, right? Send. How do you send it? How do you send it? How do you send a byte?
Toggling the light.
Yes? We have to know the big picture first, right? How to send it?
You need your start bit, which pulls it low,
Mm-hmm.
and then you do all your bits in between,
Mm-hmm.
and then you do your stop bit, which pulls it high.
Data. Right? That's how to do it. That's what you want to do for the ISR. So is this, can I do, is this one byte or I can do like one stop and one start and one stop and I have like multiple bytes in the middle? One byte. Keep that in mind. One byte only. Super important before you want to start programming. All right. So that's a big picture of what you really want and you have to implement it in C, embedded C code. How do I pull it down?
Turn the LED on.
Percent LED pulses.
PWM, what? There's don't remember the full name, but PWM, LED what? Remember the PWM?
Isn't a PWM like low value LED on?
What does this mean? It's a really quick check to see if you guys are coming to classes, right? So in the final exam, problem number 1, nothing, no description. I'll just draw a picture. What is this?
That's showing that when you have pulses, that's a logic 0
Yeah.
in the decoder.
Okay.
So pulses from the LED give a 0 to the decoder.
Okay.
And
So LED what?
on.
Because LED on will turn on the PWMs, right?
Yeah.
Will give you a 0 volts. At where?
The decoder.
Decoder is what?
Research.
Output, right?
Yeah.
Decoder's output is connected to where?
PC. Or
RX what? Or RB what? RB, RC, RX. Final exam problems, right? Problem number 1, no description. RB what?
7.
RX what?
2.
Any questions on this by far? Okay? What's that?
So you want us to memorize which pins specific components output to?
I was joking, but
Okay,
there's
I was
probably
like-
will be a data sheet or a diagram. I will draw, like show the.
Okay, I was like, oh no.
Yeah. Make sense? Okay. Now let's start working on the state machine. Okay. Let's work on the state machine. Even though you already finished Lab 7, it's still a good learning process, okay? Just go through that in your mind. It's good. I couldn't even memorize it, but every time I go through this, I learn something new, okay? So what's the first state?
Idle.
And there's the flag, right? What's the name of the flag? It doesn't matter, okay? So it's called transmit. Start. Flag.
Oh, sure.
It goes to itself. There,
0.
yeah, so when it's
When that's false.
false, it moves to the next when it's.
True.
So next state called TX
Start.
start bit. Okay? So what is the start bit? This guy. Okay? What you do?
You gotta turn the LED on.
You don't need a cheat sheet for this, right?
No.
This will be on the exam. No joking. LED what?
On.
Okay? Why? Because the decoder designed that way. What's next? You're gonna move to the next state. Otherwise, it's gonna stay for forever. Data. Data bit, right? What else? Let's come back later, okay? TX data bit. Okay?
Oh,
So
and the start bit, make your mask.
yeah,
Initialize
yeah.
your mask.
Initialize
Same as the.
mask. As what? Why don't you want to initialize over here? Why not here? Why? I mean, this brings up another good question.
You're changing states, you don't want to have to create a mask. Like you have to
Yeah,
change
yeah.
the mask.
You're not resetting the mask, right? You want to reset the mask.
Yeah.
Because next time you come to here, you want to have the mask already shifted. It's gonna still keep shifting. If you initialize the mask over here, you're always getting the initialized mask.
Just the
That's why you want to
value.
split them into different states. That makes perfect sense. You have state machine. Okay? How do you initialize mask? As what?
Mask equals 0xb.
Bunch of zeros.
Or, yeah, 0B, 000001.
0B or 0B, right?
8 bits with the last one being 1.
All right, 0B. Why 1 here? Why 1 here? This could be another quick quiz question. Just testing you guys if you understand. Why 1 here?
Just that's what.
You start with LSB, right? Start extracting. And to the AND logic, you are extracting every single bit, starting from the LSB. AND it, extract it. AND it, extract it, shift. AND it, extract, shift. I'll show the piece of code very quick after this, okay? You'll see how that works. That's another super important snippet of code I'm gonna put on the exam in the future as well. You just need to know all these important functional blocks. So in here, what should we do in here? What are the different cases? Let's talk about, discuss the mask, okay? What you wanna do, if mask is 0, what does that mean?
That means it's already shifted.
Shifted out. Good. Okay. What does that mean? If it's already shifted out, what you want to do?
Change state.
Which means all the bits in the byte is already extracted. You're done with that byte. You want to move to the next. You want to move to the next state.
So go back to start bit.
No, there's another state. We'll talk about that real quick. You'll know why do we need that. So move to another state, which is called TX stop bit. Okay? Which is here. But let's finish this first. So update the state. What else?
Shift mask left.
Oh, so that's in else, right? If it's 0, do this. If it's not 0, what does that mean? It's still shifting. Still shifting and extracting. Still in the process. What you want to do here? It's a functional block. Keep in mind all the functional blocks I'm talking about. You want to know what they're doing. Do what? Shift and extract. And what?
Turn off or on LED. Basically.
Yeah? Depending on what you have, right? If you got a 0, what you want to do? Exam question. If you got a 0, you're doing the AND logic, right? You AND it, you find a 0. It's the result of 0. You want to send a 0, right? You want to turn LED on or off? You're getting a 0, right? Should be on, right? See? On give you a 0. Is that right?
Yeah.
Okay. So you know when to turn on, when to turn it off. What else? So else, which means, so if mask is 0, go to the next state. If it's not 0, let's do the shifting. Let's extracting and shifting, turn on the LED on and off. What else? Shift it, right? You have to shift it somewhere. You just have to shift it somewhere. Okay, you shift it. After you are done, you shift it. Immediately, you shift it. Okay? I think this covers all the cases. Now let's go to the stop bit. So in the stop bit, we want to discuss the condition here. So if the data, okay, the data is called transmit IR buffer with the index here I. If this is, we're gonna use null as a condition to discuss. If it's null, what's gonna happen? What you wanna do?
Go to the next.
What does that mean if you get a null here?
It means that
So the null is already shifted and detected, right? If it's a null, it's all 0, but however, it's already, it has gone through all the process over here. So what you wanna do?
It means that your message is over.
But you still need to check sum, remember? So when you're at null, after null, it's gonna be checksum. Remember the checksum is for error checking purposes? You have another one after it. So where do we wanna go to? You wanna go back here. So it's able to take out another one and do the shifting for null, for checksum, right? So state should go to the beginning, TX Okay?
And then you're gonna wanna also make a flag that.
Yeah, make a flag. It's called TX checksum. Because next time it comes here, it won't do this anymore. It's gonna do the another one because it's now next time it will be checksum. It's not null anymore, right? So checksum equals true. Okay. And else if, because when it's null, go back here, do this, get null, transmit it, and then come back here. It's not null anymore. It's gonna come to else if. Else if tx checksum is true, because you set it true previously, what you do? If it's true, what's gonna happen? If your checksum is true, what's gonna happen? Checksum. So when you reach here, which means checksum is ready to transmit as well. Done. Go where? Idle. What else?
And set checksum to false.
Turn it false. Yes. What else? That's it for now. Okay. So else. What does else cover?
Everything else.
Everything else. Good answer. So else covers everything else, means everything else in the data, not null, not checksum, but regular data points. Okay? So what you want to do here? If it's regular things, what you want to do? Where should you go?
Start bit.
It should be start bit as well, right? Are we missing anything? Are we missing anything? That's the best part of this class, of this lecture.
Okay.
I mean, go through everything's easy, but what are we missing?
Write the timer to however long.
Oh,
length
the
is.
timer is something like by default. You should know how to do it,
The
okay?
receiver
But that's
and
something
the
else.
transmitter
I mean, the
goes.
functional things over here. The timer will be written at the bottom.
Because you need to specify the receiver and transmitter.
So first we need to increment I, right? So the index should be incremented.
Mm-hmm.
Uh-huh.
Yeah.
What else? It's called stop bit, but did you really stop it? Did you really stop it? Did you pull it up? Where did you put it up? Let me know. Where did you put it up?
We did.
Hmm?
So in the TX stop bit, that's when you get into that state.
Where? Here?
Yeah.
Here? 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 Where?
Right above the if statement, just pull it high.
Wait, no.
LED what?
On, off. Yeah, off. My bad. I spoke before I thought.
Off, right?
Yes. Anywhere else we should place it, we can place this too. So this, I'm curious, try it. If it doesn't work, put it somewhere else. But I think it's gonna work, it's equivalent. So in the solution, it's being placed in a different place. So where else we can place it?
You could put it in idle.
Yeah, that's right.
Where did you finish the byte, transmission of 1 byte? So where should we put it? Logically. Right after this, right?
Yeah.
It's 1 byte. Right after this, put it up.
Oh, so after
Where?
you're done shifting the mass.
Where? Here, yes, it works because you are done with the data transmission, but you didn't turn it off anywhere here. So right after that, in the next state, you do it on the top. Good. What else? Where else you can?
If mask equals 0, because then you know you've gone
Yes.
through all the bits.
Here
Uh,
doesn't matter, right?
Yeah.
I don't think that matters. So could place here as well, right? Okay. What is this? LED off. Okay. Anything else we're missing? One more thing I have to talk about. Any questions on this before we move to the next topic? Still same topic, but slightly different. Any questions?
Earlier you had in like the message thing less than 3. I had less than 4 because
It doesn't
you-
matter. Yeah.
Doesn't matter.
Doesn't know.
Okay.
As long as it's not. Yeah, it's just depending on if you are using all of the memory banks, right? Doesn't matter.
Okay.
Just leave the space for the checksum and null in there. Okay. One more very quick comment before we call it. Okay. Should I show you that? Let me see. Okay, here. This is the ISR we just went through with the state machine. So it's a timer 1 ISR. So how the time is being determined? Definitely by timer 1. So here's the timer 1 setting. Okay. Makes sense, right? Every time it breaks, it reaches here and set up a time. So whenever the timer is up, it triggers the ISR and comes back to the ISR and do whatever in here and break. So after it breaks, it's not going to run the following states. It will directly break from all the cases and directly reach the bottom, right? That's the fundamentals of C language. So another thing you need to know is, I'm going to show you this really quick. If you go to here, this guy, not that guy actually.
The Getch.
No, here. So you can name it whatever you want. My ISR, or digger ISR, whatever ISR, but eventually it's going to call this function, just a pointer pointing to this ISR. This is a real ISR running internally. See what's happening at the very top. Whenever ISR is called, what's happening? Flag is what? Flags are cleared. So whenever it calls ISR, flags what? Is set. Because timer's up, flags 1. Calls ISR, comes into ISR, do what? Cleared by itself. So if we come back to this code, let me ask you a question. So question on the final exam, is this necessary?
No. But it's nice.
Well, I mean, you take time while you're inside.
Is this necessary?
Yeah.
Why and why not?
Well, the reason I would think it might be necessary is because you're taking time while you're in the ISR to do whatever you're doing in there.
But there's nothing to do with the flag, right? This is way shorter than whatever the timer is setting.
Oh, then.
This is like just several microseconds.
Oh, then no.
This is unnecessary. Remove it, run the code, same results. I tested. Because what? One little question there. Why? Yeah, because the ISR clears it itself. Make sense?
Just
Okay.
as long as you're not doing something like printing in your ISR.
Okay. I'll see you guys tomorrow.